Hi, I am Shivani of CSC D section. I'm going to talk about operating system, a low overhead dynamic management system for constrained memory embedded system. Introduction: all the technologies such as asymmetric digital subscriber line and cable modems are increasingly common for internet access. Very large numbers of users still depend on dial-up modem connections over telephone lines, and this will continue to be the case for the foreseeable future. Due to the low cost and ready availability of such connections, the design of equipment to support such uses is therefore of continuing interest and importance. Multi-channel data modem software: the performance of modern digital signal processing chips is good enough to allow them to execute multiple instances of the modem software at the same time. We refer to each such instance of the software as a modern instance. Each modem instance corresponds to one hardware port for data exchange with the users. The data received from the user is passed to a router for onward transmission on higher speed connections. Single instance modern software units: the progress of a typically call is as follows. Initially, the modem instance is an idle state termed instance control. On receipt of a call, the modem instance changes state to one of the connection established states according to the session protocols requested by the user. Dynamic memory management: in this paper, we focus on a dynamic memory management system for an MMD system. This real-time system is running multi-channel data communication software. Strict and urgent performance requirements are placed on software used on embedded systems. Such systems are process time dependent. They have to meet real-time constraints of the auction execution process because they are applied to make control over time critical real-world environments. The algorithms: a large number of dynamic memory allocations algorithms are available, and it is impractical to evaluate all of them. In this work, we focus on the most promising allocation policies, namely first fit and best fit. These two allocation policies were chosen to investigate through state-of-the-art technology in dynamic memory allocation. This survey proposed different implementation mechanisms that optimize the speed, freeing speed, memory fragmentation, and effective used memory. Choice of an implementation mechanism: choosing a good implementation strategy to match the memory allocation strategy of the application program is one part of a good allocator. Choosing the right mechanisms for implementing the strategies is as important for an allocator to match the crucial criteria of the application program. With well-behaved implementation mechanisms, the allocator can be optimized to maximize the effective used memory, keep fragmentation low, and keep response time below an acceptable limit. Header fields: address ordered free list. This header field already implements an address ordered linked list needed by the fit first and best fit allocator to search for the first or best fitting block. Recording the size of each block in the header field makes it easy to calculate the start of the following block, that is, to create a linked list. Boundary tags: coalescing performs merging of free blocks in memory. Every time a block is free, its previous and following blocks in memory. Implemented algorithms: the choice of both the first fit and best fit strategies with the boundary tag implementation mechanisms led to the implementation of the four different dynamic memory allocation algorithms, namely first fit address ordered free list, first fit address ordered free list without boundary tags, first fit address uh, ordered free list with a model of software running on the embedded system emulating the memory request reclamating stream of the real program. Evaluating memory allocators. In this section, the four allocators are evaluated with the model of the software running on the embedded system. This model stimulates software units of the real application in the way they requeue, stand, release memory. Efficiency of main memory use. The following results were obtained for the worst behaving allocators, that is the best fit. Efficiency of memory use 97.8%. Memory used for uh, header fields and memory fragmented. Time efficiency of allocation functions. The first fit strategy takes less time to manage memory than the first fit strategy. In absolute terms, the slowest strategy, best fit slow free, takes us to allocate a block in memory and reclaim it. The best strategy, first fit last free, is indisputably faster. The slow free strategy is faster when performing swapping. Size of the allocator implementations. Finally, the size of the executable allocator module is also of interest. The size of the compiled software is shown in table 3. The next row gives the size of the program. Text segment. Data row indicates the size of initialized data segment, and the BSS row gives the size of uninitialized data segment. Conclusion. In this paper, we examined four different dynamic memory allocation algorithms for use in an embedded system running multi-channel data modem software. We examined two different implementation mechanisms for two well-known dynamic memory allocation strategies, namely first fit and best fit. References. Thank you.